Hello, this is Team Matt, and our project for CNEE C159 is integrating student learning and improved green infrastructure at Sherwood High School. So, a little bit of background information on Sherwood High School. Like many built environments, it has impervious surfaces which impede natural retention and infiltration of runoff and lead to flooding, erosion, and water contamination. By introducing green infrastructure, we can reintroduce vegetation to the urban environment, reduce runoff, and bring educational and societal benefits for the local community. So, a little bit of regional context on Sherwood High School. It's located in Sherwood, Oregon, which is a small residential community about 15 miles southwest of Portland and only has a population of about 20,000 people. Sherwood receives around 42 inches of rainfall annually, with a peak rainfall season in winter and a dry season in summer, and the city sources most of its water from the nearby Willamette River. So, this high school that we're focusing on is actually a new Sherwood High School, which is currently under construction to replace an old Sherwood High School. So, the students from the old Sherwood High School will be going to this new one, which would be around 1,700 students. The majority of these students come from middle class or affluent families, as only 15% of these students qualify for reduced or free lunch. On the site, the main soil is silt loam, which is composed mainly of silt and clay, but contains around 20 to 30% of sand as well. And so this soil is moderate to poorly drained and has slow permeability. And the vegetation at the completed site, according to the construction plans, will consist of approximately 40 acres of various lawns, around 1,300 trees, 5,000 shrubs, and 555,000 herbaceous plants.
Next, we get into runoff characteristics. In this slide, we calculated the peak flow runoff using the rational method. In order to do so, we firstly determine the runoff coefficient. According to the United States Green Building Council, hardscape ranges from 0.7 to 0.95, while softscape ranges from 0.05 to 0.35. We then followed a common general rule and set our impervious surfaces to be a coefficient of 0.9 and pervious surfaces a coefficient of 0.3. In order to figure out the rainfall intensity, we had to look back at the information from our previous rainfall data. As a result, we noticed that rain peaks in Oregon during the winter, based on the average of the winter months. For accounting for capturing larger storms, we get an intensity of 6.6 inches per month. When converted to inches per hour, the value comes to about 0.00904. Peak flow is lastly determined by multiplying the runoff coefficient by rainfall intensity by the square footage of the area. Q equals C times I times A, and all our calculated values are displayed on this table. Another set of calculations we performed were the runoff volume calculations for each drainage area. This is determined through the curve number method. Some input factors that we made were categorizing our hydrologic soil group to group C because the area seems to have moderate or poor draining soil, setting our standard moisture conditions to 2, and accounting for a 25-year, 24-hour duration design storm to comply with the City of Sherwood Stormwater Management Plan. On the right is a table displaying all these values. Later, we then look at some observations from the topography layout of our project. Noticing by the detailing of the contour lines, the site we are dealing with is pretty hilly. It also seems to be that elevation is flowing down the direction of the map as seen with the red arrows. The flow is towards two low points of the site, which is actually where the existing extended dry basins are located for capturing storm water. Some physical contaminants that may be present in our job site includes sediments as a result of heavy construction and temperature change due to heat transfer from the roofs or asphalt concrete to the stormwater after exposure from the sun. Some inorganic contaminants include fertilizers if the school decides to implement lawns for the sporting grounds, and heavy metals after contact with the buildings and bleachers. There are no organic pollutants, but wastewater may be considered treated if necessary. And now we get to the existing stormwater plan. Here is the existing plan to manage stormwater at the high school. It consists of extended dry basins at the northeast corner of the site to capture minimum water quality volume and detain the water for the 48-hour drawdown time, as defined by the Clean Water Services Guidelines. For Sherwood High School, we calculated that the water quality volume captured by the extended dry basins is approximately 52,850 feet cubed. These calculations are located in the appendix. Although it reduces stormwater runoff, the current plan does not take advantage of educational purposes or rainwater reuse.
So next, we're going to discuss the modified stormwater plan to improve upon the plan that's already there. This consists of two different parts: using the roof to capture rainwater for reuse, and creating rain gardens to both reduce the amount of runoff and incorporate green infrastructure. Sherwood High School has a lot of roof space, nearly 180,000 square feet. Instead of letting rainwater either pour off the roof to join ground runoff or get trapped on the roof and evaporate, we suggest installing two large cylindrical basins to store the rainwater coming directly from the roof. Both are located at strategically lower locations of the roof's design to utilize gravity to help the water flow in their direction. Sherwood receives many inches of rain per year, which when multiplied by the area of the roof, results in a lot of roof runoff. Even if the collection basins don't capture every inch of rainwater falling on the roof in total, they still have the potential to collect thousands of gallons of water. To the left, you can see the rough design for the rainwater harvesting system. Gentle inclines will be installed on the roofs to encourage the water to slope towards the basins. Gutters will be in place to both control the flow of water and prevent larger debris such as leaves from getting in the basins. The water then travels straight from the roof to the basin via pipe. The potential amount of rainwater to be collected from the roof exceeds the capabilities of the school alone to use, but a possible solution would be to sell or donate the water to other local companies who may benefit from an easy supply of rainwater.
The second part of the modified stormwater plan is the rain garden situated throughout the school. As you can see in this figure, we can split the school into 5 main drainage areas and place rain gardens to capture part of the runoff from each drainage area. For example, for drainage area 3, water from the parking lot will drain into the vegetated soil in the bus turnaround before being carried by subgrade pipes to the rain garden, where the water will be captured and stored. The rain gardens are designed to capture a total of approximately 262,000 cubic feet of stormwater runoff. We plan to further improve the school landscape with these rain gardens by planting native species such as Douglas aster, Baltic rush, and Highland cranberry. The modified stormwater plan thus presents many benefits. First, it captures significantly more runoff than the existing plan. As this table shows, the modified plan captures approximately 5 times more total runoff from the site. This means less overland flow, lower risk of flooding during long periods of rain, and more treated stormwater. Secondly, our modified stormwater plan presents many educational and communal benefits. Not only will students see how green infrastructure works on their campus, teachers can also introduce concepts in hydrology, stormwater runoff, water treatment, and local ecosystems in the classroom. Additionally, students can volunteer to help harvest plants, remove weeds, or maintain the rain gardens and rainwater capture system. The water captured from the rainwater harvesting system can also benefit the greater community through reuse at local businesses. Thus, the school can strengthen ties with the community. Finally, the green spaces themselves, as many studies have indicated, will also improve mental health throughout the community.
Our conclusions from the research we have done are several. We first want to acknowledge that Sherwood High School does have a good current green infrastructure plan in place, but it can be modified to be even better. These modifications include adding roof rainwater capture systems and bio-infiltration basins, as well as allowing more opportunities to learn about and gain experience with green infrastructure for the students. Green infrastructure is needed now more than ever in a world that is becoming increasingly urbanized. Projects like this are essential in educating, inspiring, and improving not only our society, but the entire globe. Thank you so much for your time.